to 3.1 and the beginning of our new unit called the atomic theory. And in this video, we're really just going to be talking about how we came up with our current view of the atom. This is obviously a picture of what our current view of the atom looks like, where we have, a small dense nucleus, we have electrons spinning around the outside. So what we know about matter is that all matter is made up of atoms, and that there's a lot of different types of atoms. Currently there's 118 different types of atoms. We call those elements, and we see them on the periodic table. The atom is essentially the building block for matter, so that's really where we're going to start in our study of chemistry, is with that building block. Okay, so let's go and talk about what helped us to create our current view of matter. This first guy I'm going to talk about is Democritus, and Democritus lived right around 400 BC, so this stuff happened close to 2,400 years ago. Democritus had this really interesting thought, and you have to remember back in the day, 400 BC, experimentation wasn't a thing. They never experimented to find results. They theorized in their head. They used logic and reasoning to determine truth about the world, which now, when we think about it, sounds kind of ridiculous, but back then, that's just how it was done. And so Democritus, he had an apple, okay, and he cut the apple in half, and he thought, wow, I have 2 pieces of apple now. And then he cut that apple in half, and then he had 4 pieces, and then he kept cutting the apple until he couldn't cut the apple anymore. And he thought to himself, he said that matter could not be divided smaller, that eventually the smallest possible piece would be obtained. And so he called that piece atomos. Atomos meaning cannot be cut. So he's the one who first came up with the idea of having an atom, the building block for matter, the smallest piece. Really, his ideas were kind of put to the side for a long period of time, close to 2,000 years, until this guy named Dalton came along the scene. So let's recap. Democritus basically came up with the idea that matter is composed of teeny tiny undivided particles, okay? And we call those particles atoms. Well, Dalton did more experimentation and came up with what he called his 5 postulates. Postulates are like theories. Sorry, they're not really theories. They're hypotheses about what he thinks the building block for matter is. So these are his 4 ideas. The first one is, he kind of basically stole this one straight from Democritus. He said matter is composed of indivisible particles known as atoms. So again, this is kind of stolen from Democritus. And the second thing he came up with was that all atoms of a particular element are absolutely identical. For example, all H atoms look exactly the same, okay? And all carbon atoms look exactly the same. And all oxygen atoms look and weigh exactly the same, okay? The third thing he came up with was that different elements are made of different atoms, okay? So for example, H atoms are different, or hydrogen atoms are different from carbon atoms. Okay, so he came up with the idea that atoms of different elements are different. He didn't know why they were different. He just theorized that they were different. And then the last thing he came up with was that essentially you cannot destroy matter. He says in a reaction, the atoms can be rearranged. They can form new things. So hydrogen and carbon could form something, and then they could break apart and they could form something else. But you still have the hydrogen and carbon atoms. They're just being rearranged, okay? Kind of like how you have Lego pieces, and you can put the Lego pieces together, but you can't actually take a Lego piece and then make it disappear, right? You can only rearrange it in certain situations. And so he said you cannot destroy atoms into different elements. Now we take Dalton's theory, and we are going to analyze it because there's some problems with his theories. There's actually 2 parts of his theories that are not considered part of the modern view of the atom, and that's important. The modern view of the atom is that we can divide an atom, right? We can make it into smaller parts. What are those smaller parts that we can divide an atom into? Well, we have protons, we have neutrons, and we have electrons. So the atom can be divided, so that's why this first one's considered incorrect. The second thing he says is that all atoms of a particular element are identical, and that's actually not true. What we know now is that of all the hydrogen atoms found on the world, each hydrogen atom can be slightly different from another hydrogen atom. We call those isotopes, and we'll talk more about those later. But essentially, an isotope is the atom of the same element, but has a slightly different mass. The third postulate he came up to is correct. So good job, Dalton. You got one right. And then the last one, it is correct, but it's kind of not correct. And you don't need to know this for the exam. For the exam, let's pretend this one's correct. But technically, you can take an atom and you can make it into a new atom of a different element. Like you can actually destroy that one and create a new atom. And that's through nuclear reactions, which we'll talk about way later in the year. And that's when we talk about atomic bombs and fun things like radiation. But for now, we're just going to pretend like this one is true. Okay. Moving on. So we have Democritus. He says, you can cut down an apple until you get a tiny particle, and that particle is going to be the atom because it's tiny and it's indivisible. Dalton came along the scene in around the 1800s, and he said, I have 4 things that I know about matter, and I know about atoms. And 2 of them were wrong. The one that was wrong is that matter can be divided into smaller things. And the second is that all atoms of a particular element are not identical. Okay, they have different masses. So this is kind of our modern view of the atom. It's another picture. We know an atom consists of protons and neutrons. They're found in the very center. And we know the outside of the atom are made of electrons. They take up that space. We did not always know that, though. So where did we come up with the idea of a proton and electron and a really small nucleus? Well, let's go back in time, and I'm going to talk about this guy named J.J. Thomson. In around 1897, he did an experiment called the cathode ray tube experiment. And that's a word you're going to have to know, cathode ray tube. Essentially what he did is he created an experiment, and he put gas in here, okay? So he put a gas that was neutral. Do you guys know what neutral means? Neutral means that there's no charge. So sometimes you can have, remember protons are positive and electrons are negative? Well, if I have the same number of electrons and the same number of protons together, there's no charge, right? They balance each other out. But if I have more electrons than I have protons, then my substance is negatively charged because electrons are negative. If I have more protons, then my atom's positively charged because protons are positive. So he puts a neutral gas, which means there's no charge. There's not a bunch of electrons and just a few protons. It's all neutral, okay? There's no charge. So what's interesting is he ran electricity through this tube. Okay, so I'm going to draw electricity with this orange. He put electricity and he ran it through the tube. And what we know about atoms is that they have electrons on the outside. And guess what? Those electrons are negatively charged. So he put this electricity through the tube, and I don't know if you can guess what happens or not, but he noticed that electrons were being released in the tube due to the electric current running through it. And so this was like a huge discovery. He said that negatively charged particles, remember, he didn't know what electrons were and he didn't know what protons were, but he said something negative is popping off of this neutral atom. Okay, so these are some of his thought processes. This is his observation. He observed that negative charges come inside the atom. So in the atom, there's something that's negative, which means that there has to be a particle in the atom that's smaller than an actual atom. That is negative, okay? So this is where he disproved Dalton's postulate that an atom was indivisible, okay? Because he figured out that an atom was actually made of things that were smaller. So he disproved Dalton's theory right here. Okay, so the first thing he observed was that the negative charge was inside the atom, and then it's got to be its own thing. It's got to be something. So he called it corpuscles, also known as electrons. That's the negative thing that was popping off. Now, let's think about this. If something negative is popping off of an object that's neutral, that means that there has to be a positive particle somewhere in the atom to make it neutral. If there was not a positive particle in the atom, then our atom would not be neutral. It would be negatively charged. So we know there's a negative, right? Inside the atom, there's a negative particle. In order for it to be neutral or a charge of 0, there has to be a particle that's positive to even it out. That was his follow-up question. Since the gas was known to be neutral, having no charge, he reasoned there's got to be positive particles in there somewhere, but he never found them. So he developed what's known as the plum pudding model. This is what he said. He thinks the atom is a positively charged substance, and inside of it are these negative electrons kind of interspersed everywhere. So this would be the positively charged proton substance, kind of like a gel, and in the gel are the electrons. And he called it the plum pudding model because this is what plum pudding looks like. And plum pudding has like little raisins scattered about in the pudding, kind of like the electrons are scattered about in the positively charged substance. So we know that's not correct, right? We know that we don't have electrons everywhere. We know that we don't have a positively charged pudding substance. So how did we get to our current view? Well, this guy named Rutherford, who is one of my favorite scientists of all time, and I really have such a crush on him that I named my cat after him. So Rutherford decided, this is actually totally unrelated to chemistry, but he decided to take a little piece of gold metal, okay, foil, and he was going to shoot at the gold foil protons, or positively charged protons, okay? Now, that's important because if the plum pudding model is true, then remember these are positive charges. Remember, positive and negatives don't like each other. They kind of go away. So, I'm sorry, that's not true. Positive and negatives attract each other, and then positives and positives will repel, and negatives and negatives will repel. So he said, if I put all of these positive charges through, if this whole blue thing is positive, and it's kind of like positive throughout, then it's not going to affect the charge. But the charge will slightly go towards the negative. And then you can see this positive charge goes slightly towards the negative. So see how all these rays are bending? They're bending to be closer to the negatively charged substance. So he basically thought my positive rays will go all the way through an atom, right? They're going to go all the way through because everything is evenly charged in the atom. However, that's not what happened. This is what actually happened. When he put these, remember, all these are positively charged rays. Most of them went all the way through because, the reason why is because the atom is made up of mostly empty space. Okay? So because the atom is made up of mostly empty space, the positive rays didn't hit anything. So they would go all the way through. A few of the rays would get near an electron, and so they bent just a little bit to be closer to that electron. Because remember, positives and negatives want to be next to each other. But so most of the rays went through. However, every once in a while, some of those positive rays would hit the positively charged nucleus. We know that the nucleus is very, very, very dense, okay? And we know that that nucleus is positively charged because we know inside of a nucleus there's protons that are positive and then there's neutrons that are neutral. So the only charge inside the nucleus is positive. So what happens when a positive and a positive come together? They repel. So that's what happened here. We see that this positive charge hit the nucleus and bounced off because it was repelling the nucleus. We see this ray bounced off and repelled the nucleus. So most of the rays went all the way through, but some of the rays were greatly deflected. And that's a term you're going to want to be familiar with. Deflected means like bounced back. So this told Rutherford several things. It first told him that there's a small, dense, positively charged center. Why did he know it was small? You might want to write this down. The reason why he knew it was small is because most of the rays went all the way through and never touched the nucleus, which means that nucleus has to be tiny. How did he know it was dense? Well, something that's super dense and super positively charged would greatly reflect a positive ray that hit it. And so we know that it was dense and it was positive because those rays that were hitting it got greatly deflected. So he called the center the nucleus, and he figured out that the nucleus is very, very small compared to the rest of the atom. So this is kind of now our new idea. He reasoned that all of the atom's positively charged particles were contained in the nucleus, and the negatively ones were scattered around the edge of the nucleus. And that's all, folks. Goodbye.